Well, happy Monday. So today what I'd like to do is talk about absorption. And as I mentioned, we have been talking about adsorption. We're now talking about absorption. So we're talking about a surface. So absorption typically into the micropores of a surface. Now we're looking at gas-liquid transfer. So we're looking at transfer from a gas to a liquid. Typically, we're looking there at soluble organic compounds. For example, CO2. We can absorb CO2 from a gas stream into water. Ammonia, chlorine, we typically do that in water treatment, for instance, or wastewater treatment. SO2, so we use it for desulfurization of the gas stream and removal of SO2. Or we can transfer a chemical from a liquid into the gas. So for instance, if we have groundwater that's contaminated with trichloroethylene, tetrachloroethylene, we can then transfer that chemical from the groundwater into the gas phase, and then we can subsequently treat it in the gas phase. So what we're looking at here is a mass transfer process. So shown here is in terms of SO2, but we can think about this in terms of any of the gases previously mentioned. So we have SO2, and shown here is in the gas phase, and that SO2 molecules are then brought to the surface of a liquid film. So think of this as water droplets. We need to have mass transfer across the air-water interface, and then we have dissolution of the SO2, which then reacts to form H2SO3. We can also have, we have really SO2 gas that's dissolved, then can diffuse the other way. Think about this in terms of water. So just let's think in terms of a river, and we'll think about this in terms of oxygen. We have oxygen in air. That oxygen can diffuse across the air-water interface. Now we have aqueous oxygen, so that oxygen is dissolved. So we have, typically we describe this in terms of the partial pressure of oxygen and in terms of a concentration of aqueous oxygen. Now the rate of gas transfer depends on a number of factors. Think about it in terms of the red cedar and oxygen transfer. So the rate of transfer is a function of what? What factors affect the rate of transfer? Or are there places along the red cedar where you think the rate of mass transfer is going to be the greatest? Where would that be? Think about the red cedar as it moves through, as it flows through campus. Where would the rate of transfer be the greatest? Okay, so here. Okay, it's at the weir behind Wells Hall where the flow is turbulent. Exactly. So typically, where you have turbulent flow, you will have the greatest rate of transfer. So it's a function of, I'll just refer to this as mixing, or we can think of it in terms of turbulence. In terms of whether the water is shallow, you've got more surface area across which that mass transfer can occur. So we'll refer to this as a surface area. What other factors are likely to affect mass transfer? Exactly, temperature. Anything else? Both the partial pressure of the chemical and the concentration in the aqueous phase will affect the rate of mass transfer. So those are important factors, and we need to consider those factors when we're thinking about the design of these absorption systems. So in terms of designing these, we have some parameters that we don't have as much control over in a natural environment like the red cedar. We can control the ratio of the liquid flow rate to the gas flow rate. The solubility of the gas will play a significant role also in the efficiency. We talked about temperature, both temperature of the gas and the liquid. And then the ability to contact, and we've talked about this in terms of turbulent flow. So all these are extremely important in terms of the efficiency, and we'll add surface area. Now, in terms of the processes, they're essentially the same processes that we talked about with wet scrubbing. The difference when we're talking about wet scrubbing, we're looking at the removal of primary particulates. Now we're looking at the removal of chemicals. So the design of the systems are somewhat different, but the operation is essentially the same. So we talked about spray towers before. Operation is exactly the same. We have some sort of a spray mechanism, not typically conical nozzles, and we're spraying water. So you see we have the air flowing upwards. We have the liquid flowing down. We're providing for contact between the air and the water, and we have clean air out the top, and we have our water containing containing the chemicals out the bottom. So this says particulates here, but it's whatever chemicals we're looking at removing. The graph on your left gives you an idea of how the liquid flow rate, so L being the liquid flow rate, G being the gas flow rate, how that ratio affects removal. And you can see that as we increase the ratio, the liquid flow rate to the gas flow rate, our removal efficiency increases, and eventually will actually asymptote out. So there's a point of diminishing returns. You're not going to get the removal efficiency or increase in removal efficiency that you would get with a lower ratio. So for instance, if we look at a ratio of 25, we can get maybe about 40% removal. We double that to 50, we get about 70% removal. So we're going from about 40 to 70. But then when we double from the 50 to 100, we're only going from about 70 to maybe 80% removal, somewhere in there. So you can see, we really get to that diminishing return. This is used typically for removing chemicals that are very soluble and where we don't need very high removals. If you need 90+% removal, you're not going to use a spray tower. You're simply not going to get the removal. Now we can also operate these in multiple modes. We've talked about, shown here is a co-current mode. We can also operate these in a counter-current, which was the previous slide, or a cross-flow mode. And this can be used for flue gas desulfurization, so to remove that SO2 from a gas stream. We can also use packed columns. Now, Again, same as what we've talked about previously. What we have is we have a chamber. We have some sort of packing in that chamber. You see, we have a way to distribute the liquid, to try and distribute it equally so that we have good contact. The packing material can be plastic, it can be PVC, it can be polypropylene, it can be ceramics, it could be metals. But it's a type of material where you have a significant amount of surface area. So you can see here, for instance, this, you see all the, it's almost like a ribbon. And what we have is significant surface area across which the water can distribute and the air can diffuse, or the chemicals can diffuse across that mass transfer interface into the liquid. So again, we can operate these in co-current, counter-current, or cross-flow mode. We can use these for a number of different situations. So we can use this, for instance, to control hydrochloric acid or sulfuric acid from pickling operations in the metal industry. It's used to control odors in rendering plants and petroleum refineries, and can also be used in sewage treatment plants to control odors. Tray towers, again, similar to what we've talked about before. We have some sort of an impingement device. So water is flowing across these towers, through these towers. You've got these trays. It's causing the water and the air to foam. Again, we've got strong, good mass transfer. And you can see we can use these because of the increase in mass transfer. We can use these for sparingly soluble gases. Typically, these are run in countercurrent mode. And then finally, we have the Venturi Scrubber, again, similar to what we talked about before. These are typically used when you're removing particulates and the gas. And you'll, sorry, these typically have much higher pressure drops than the other units that we just looked at. So again, the unit is essentially the same. The difference is previously when we talked about wet scrubbers, we were looking at removal of particulates. Now we're looking at mass transfer of a chemical across the air-water interface. So in order for absorption to occur, we need to have that pollutant diffuse from the bulk phase, either from the bulk liquid to that interface, if we're transferring from the liquid to the gas, or from the gas to the liquid if we're transferring that chemical from a gas into the liquid. And then we need to have transfer across this air-water interface, and then diffusion away from that interface. Well, the whole design of these systems is based on Fick's law, which says that the rate of transfer is equal to a mass transfer coefficient times the difference between the driving force, where Y is the concentration in the gas phase and Y star is the equilibrium concentrations, that the concentration of that chemical in equilibrium with the concentration in the aqueous phase. So we're looking at it, we're using that equilibrium concentration. And then we need Henry's law, which says that the partial pressure at equilibrium is equal to Henry's constant times the concentration in the liquid phase. So again, we're focused on looking at equilibrium concentrations and the relationship between the actual concentration in an equilibrium situation. And typically, we will use for all of the designs that we'll do, we'll use a mole fraction of contaminant in water. So the design of these systems is based on mass balance. We're back to, and we've looked at mass balance throughout the course. So think of this as we've got a column. We have contaminated gas coming in. So this contaminated gas coming in. The concentration or the mole fraction of contaminant, whatever chemical it is, in that gas phase is Y naught. So that's the initial concentration. The gas stream moves through the reactor and emerges at the top. The concentration in mole fraction of that chemical leaving that reactor is Y E. So that's our effluent. Again, these are mole fractions. We can do the same for water. So we have our water coming in, concentration of chemical in the water, we call X naught, and the water leaves, and the concentration leaving is XE, the effluent concentration. The only thing that happens is that we have transfer from, and we'll think of this in the gas phase. So we have transfer of our contaminant from the gas phase to the aqueous phase. We have no reaction. So that's important. We have no change. So for instance, if we start with tetrachloroethylene, we end up with tetrachloroethylene. Okay. If we start with SO2, we end up with SO2 aqueous. We're assuming we have no reaction within this removal device. Mass rate in equals the mass rate out. We will also assume that we have no accumulation. So we have no accumulation of that chemical in the reactor. So the mass within the reactor doesn't change. So the mass rate in the water, here's our mass rate in from the water, plus the mass rate in from the gas is equal to the mass rate out in the gas plus the mass rate out in the water. And we can write that mathematically using this expression here. So we're assuming no reaction and no accumulation. So as I've mentioned, okay, we have no accumulation, we have no reaction. We'll also assume that the flow rates are constant. We will assume that we have complete mixing within some incremental length delta Z. So within this area, we'll assume we have complete mixing. But then we have no mixing outside of that. We have dilute solutions, so we can use Henry's law. And we'll also assume that we have no changes in the volume of the air and the water. So in the transfer, we have no changes. If we had changes in volume, that would change Q and G. So Q and G in and out would not, or Q in and Q out would not be the same. And G in and G out would not be the same. So this just means that Q in equals Q out and G in equals G out. So we'll just use the terms Q and G. Now, typically when we design these, if we're looking at removing a chemical from the gas stream, then typically the influent concentration in the water is 0. So we're looking at removal from gas chemical from the gas stream. On the other hand, if we are looking at removal of the chemical from an aqueous stream, then Y naught is typically equal to 0. So for instance, if you're removing SO2 from flue gas, the initial concentration in the water stream is 0 for SO2. On the other hand, if we are removing trichloroethylene from a contaminated groundwater, then the concentration of trichloroethylene in our gas stream is equal to 0. So it's typically how the systems operate. So as we mentioned, surface area is extremely important. We need area across which mass transfer can occur. And our systems are designed to optimize that mass transfer. So A is just the area per unit volume of packing. Uppercase A is the cross-sectional area of the column. And delta Z is the differential height of the absorber. And then, as I wrote before, the rate of mass transfer is equal to, and I used an L before, that's an overall mass transfer rate, but I've written in here in terms of a gas phase mass transfer rate and a liquid phase mass transfer rate. So this is the mass transfer across the gas phase. This is the rate of mass transfer across the liquid phase. Now, in reality, unless you have accumulation, which we don't have at that interface, then those are equal. So we will assume that the rates of mass transfer across the air and water and the gas and the liquid phases are equal. This term here is your driving force. The greater the difference, the greater the mass transfer. So for instance, if you think about when we talk about, well, let's think about oxygen. Oxygen is more soluble at lower temperatures. So that equilibrium concentration is greater at lower temperatures. So I'm going to have a greater mass transfer rate of oxygen at lower temperature than I would at warmer temperatures. And note at the bottom here, I've written a number of forms of the equation. You find that different books, different resources will use different notation. So you need to be very, very careful for the notation that's used for these mass transfer coefficients. So this is just a cartoon trying to show this, what we just basically stated. So let's think of this in terms of SO2 in the gas phase. So we have SO2 in the gas phase. We have diffusion in the bulk phase. Then across the gas film interface, and then across the through the gas film, across the interface, through the liquid film, and then out into the bulk solution. And I've written Henry's law in terms of both the equilibrium concentration in the gas phase, so Y, and the equilibrium concentration in the liquid phase, X. So we'll use these relationships in the equations. The overall driving force changes, though, throughout the reactor because our concentrations are changing. So typically what is used is a log mean of this driving force. And that is simply the difference between the Y naught and the equilibrium concentration. And this is in equilibrium with XE, the effluent. Remember, because it's the countercurrent, the way we've written this. And then we have YE, so our effluent gas phase concentration. And then this is in equilibrium with X, not the influent concentration. And then we talked about the number of transfer units last week. We used the same terminology. So your number of transfer units is a measure of the degree of difficulty of the separation. And notice it's to achieve a certain level of removal. So it's the measure of the degree of difficulty of separation to achieve a certain level of removal. So when we have one NTU, that means, so if we have one NTU, that means that Y naught minus YE is equal to the log mean of the driving force. The greater the number of transfer units, the more difficult it is to remove that chemical. We can also use this expression here, which is developed for the design of an absorption unit. So slight change in and I'm not going to derive this, but it's changed to allow you to develop this or determine the number of transfer units based on the design of your system. So G is still the gas flow rate, Q, the liquid flow rate, and then M is the slope of the equilibrium curve defined by Henry's law. So we're using, it's just the constant in Henry's law. Z is the height, and that is equal to the height of a transfer unit times the number of transfer units. Note, we're using the same terminology we used with adsorption. And here, the height of the transfer unit is given in terms of parameters that would be supplied by the manufacturer. So it's related to the gas transfer rate, or the rate across the gas film, and the rate across the liquid film. If we have very soluble gases, then the liquid resistance is much less than the gas resistance. And there, this Hg or Ky, A, mass transfer across coefficient across the gas film will predominate, and that dominates the transfer. If you have insoluble gases, then the opposite's true. There, the liquid resistance is much greater than the gas resistance, and H sub L or K X A dominates. That also helps in terms of trying to think about, when do I improve mixing in the gas phase? Do I need to improve mixing in the liquid phase? Do I need to basically try and reduce the thickness of that gas film or reduce the thickness of the liquid film? So let's look at an example where we're determining the height of a packed tower that's used to reduce the concentration of ammonia from 0.1 kilograms per cubic meter to 0.0005 kilograms per cubic meter, and you're given the data here. So you're given a column diameter, operating temperature, pressure. You're given a gas mass transfer coefficient, or H sub G, H sub L, and you're given the gas and liquid flow rates. We'll assume that the incoming water is free of ammonia. So X sub 0 is equal to 0. We'll also assume that all of the ammonia is present and as NH3, we have no NH4+. It's not ionized. And we have a Henry's constant of 1.068, and that's a dimensionless Henry's constant. So I provided all the data here so that we can go through the calculations. Remember, Y and X are both in terms of mole fractions. So Y naught is equal to 0.10 kilograms per cubic meter divided by the molecular weight, apologize on the phone call, it's my mom. And then divided by the density of the air divided by the molecular weight of air. So this is the density of the air divided by the molecular weight of air. So we now have kilomoles per kilomole. And that is equal to 0.144. Y sub E is equal to 0.005. I forgot a zero. 3 zeros. Kilograms per cubic meter. Again, we'll divide by the molecular weight of ammonia. Again, divide that by the density of air divided by the molecular weight of air. And that is equal to 7.06 times 10 to the minus 4. Remember, x0 is equal to 0. Now notice we have an expression here in what we've replaced our expression for NTUs in a form that we don't need to know the effluent concentration. Only need to know the influent. A is equal to mg over q. We need G in this expression here. We need G in kilomoles per second. So G is equal to 10.0 kilograms per second. That's air. We'll divide by the molecular weight of air, and that is equal to 0.345 kilomoles per second. So that's G. Again, it's in kilomoles per second. Q is equal to 10.0 kilograms per second, and we're going to divide that by what? We need that in kilomoles per second. So we'll divide that by the molecular weight of water, and that is equal to 0.555 kilomoles per second. So A is equal to 1.068 times 0.345 divided by 0.555, and that is equal to 0.664. I'm going to switch to the next page. So let's just go back. We've got Y naught equal to 0.141, YE equal to 7.06 times 10 to the minus 4. A is equal to 0.664. So now when we substitute in here the number of transfer units, So it's just substituting in, ln is equal to y naught, so 0.141 minus 1.068 times 0 divided by 7.06 times 10 to the minus 4 minus 1.068, 0 times 1 minus 0.664 plus 0.664, that's all on the top, divided by 1 minus 0.664, and that is equal to 12.55. So the height of the transfer unit is equal to, we said Hg, and Hg is equal to 0.438 plus A, 0.664 times H sub L, which is 0.25, and that is equal to 0.604. And that is in meters. So the total height is equal to 12.55 times 0.604, or 7.6 meters. So we need something that's roughly 20, almost 25 feet high in order to achieve this level of removal. So we need extremely high column for that level of removal. Questions? We can also look at it in terms of water. And I'm including this because it's on the FE. So for those of you that are planning on taking the FE and that haven't taken 483, we've included it here. We're not going to be able to finish this today, but we'll at least start this process. So the approach is exactly the same. The difference is that if we have efficient mass transfer, then we can assume that the mass in the water leaving is much less than the mass in the air leaving. So remember, now we're looking at removing it from the water to the air. So if we have efficient mass transfer, then the mass in the water leaving is much less than the mass in the air leaving. We can also we'll assume that the mass in the air entering is equal to 0. So we'll assume that this is equal to 0, that we don't have any of the contaminant in the influent gas phase. And if that is the case, then this is small. That's negligible. And QWCN is equal to QAA out. So the whole premise of the approach that's used from water to air makes this assumption, these two assumptions here. And then it makes the assumption, again, using Henry's constant, that we can replace the concentration leaving, so this A out, we can use Henry's constant to say that this is equal to Q sub A times the Henry's constant times the concentration in the water. And then this uses what's referred to as a stripping factor, which is R, which is Henry's constant. So it's it'll be a dimensionless Henry's constant times the airflow rate divided by the water flow rate. So it's a different approach. You cannot use this approach for absorption from air to water. Okay. You're looking at air to water, you're going to use the previous approach. If you're looking at water to air, you'll use this approach. The assumptions are different. So we left off on Monday talking about absorption. We talked about absorption from air into water. We're now looking at from water to air. And as I mentioned on Monday, the assumptions for the mass balance and then the subsequent derivation of the equations that are used are different. And it's because we're shifting that the mass transfer previously from air to water and now from water to air. And we said that we can define a stripping factor, which is dependent on the Henry's constant of the particular chemical that you're looking at removing and your flow rate in the air phase and the flow rate in the water phase. And using that approach, when we're looking at water to air, so for instance, we have a contaminated groundwater, we're looking at stripping that contaminant from the groundwater into the air and then subsequent treatment in the air. Why would we do this? Because it's more cost effective in some instances to treat the air than it is to treat the water. And in this case, we can determine the number of transfer units using the equation that's given here, which is a function of that stripping factor and the initial concentration and the effluent concentration. And again, the height is equal to the height of the transfer unit times the number of transfer units. In this case, we'll define the height of the transfer unit using this equation here. Again, be very careful of the units. In this case, and with this set of equations, your loading factors again are in molar units. So it's kilomoles, and this loading factor is kilomoles per second per meter squared, per area of this packed column. And again, we use the mass transfer coefficient, which we've talked about. The approach or the concept is identical. The only difference is the issues or the direction of the mass transfer, and therefore the equations. So let's look at a situation where you're looking at designing a packed tower where you're reducing the concentration of CO2 in ground, this would be typically a groundwater, from 60 milligrams per liter to 10 milligrams per liter. Why would we do this? If we're looking, for instance, at softening that water, so removal of the hardness, the removal of CO2 requires significant chemical addition. It also results in production of sludge, and that gets us nothing in terms of hardness removal, but it costs us in terms of chemicals and it costs us in terms of sludge disposal. So we want to find a way to remove that or to reduce the concentration of CO2 so we can reduce both chemical addition and sludge production. So we have packed tower, we have an operating temperature, pressure, you have a dimensionless Henry's constant for, and this is specific for CO2. You have an air to water ratio of 160 to 1. You're told that the liquid loading rate is 0.4 kilomoles per second per meter squared of tower. the mass transfer coefficient obtained from the manufacturer is 50 inverse hours. And for simplicity, we're going to assume that the incoming air is free of CO2. So we have all of the parameters here. Just copy them over and the equations. So R sub S is equal to H prime times Q sub A over Q sub W. And I apologize, the subscripts, copying them. 0.8317 is dimensionless Henry's constant. And we were told that the ratio is 160. And that gives us a stripping factor of 133. So the number of transfer units is equal to 133 minus 133 minus 1 times ln and C in was 60 over 10. We don't need to do the conversion to molar units since we're dealing with the same chemical and the conversion would cancel out, times 133 minus 1 plus 1 all over 133. And that is equal to 1.8. The height of the transfer unit is equal to L over MW KLA. And that is equal to 0.4 kilomoles per second per meter squared divided by 55.6 kilomoles per meter cubed. So that's a molar density of water divided by 50 inverse hours times 3,600 seconds per hour. And that is equal to 0.52 U's. So the height of the tower is equal to HTU times NTU, so the height of the transfer unit times the number of transfer units, and that is equal to 0.52 meters times 1.8 or 0.93 meters. So notice, we don't have anywhere near the removal that we were required in the previous problem. And CO2 is very easy to strip from water. So the height of the tower is much, much less than what we calculated in the previous problem.